In this video, we're going to look at doing some calculus with the parametric curves. So we're going to look for tangent lines, we're going to look for concavity, we're going to look for area, and we're going to look for arc length. First up, we're going to look at tangents. So if you remember right, to find a tangent line, we would take the derivative of the function. Now in this case, my function is really two functions, so we've got to do it slightly different. So I want to do is we look at the chain rule for derivatives. We have dy over dt is dy over dx, and then times dx over dt. So we take the derivative of the inside and multiply it by the derivative of the original function. So I'm going to use that and break it down a little bit because I really want the dy dx. So dy dx is dy over dt divided by dx over dt. So we're going to find the derivative of the y function and divide it by the derivative of the x function. And if you think about that, that makes sense because it's the rise of a run. The y is the rise and the run is the x. So if we were looking for the second derivative, we're going to do a very similar thing. We're going to take the derivative of that function again. So it's the derivative of the dy dx divided by the original derivative of the x function. So we don't have to do the y again in this situation when we're looking for concavity. So in this example, we're going to look at x equals t squared and y equals t to the third minus 3t. And we're going to be looking for four different things in this problem. First, we want to show that c has two tangents at the point 3, 0, and we want to find their equations. So that means that at the point x equals 3 and y equals 0, the function actually occurs twice. So it goes through that point twice, and that's where we're going to be looking for two tangent lines. So to do that, the first thing I'm going to do is I want to figure out the points where y equals 0. So because that's going to give me those values where the y is 0, and then I got to figure out which ones are going to give me the x is 3. So if I plug in t squared, or t to the third minus 3t equals 0, I get t times t squared minus 3. And I solve those for 0, and I get t equals 0, and t equals plus or minus the square root of 3. So if we look back to my original problem, the x was t squared. So the value that's going to work, the 0 won't work because it's going to give me x is 0. The only ones that will work is the t plus or minus the square root of 3, because that would give me the 3 on my x-axis. So I have 2 points, t equals the square root of 3, and t equals negative square root of 3. That would be tangent points at 3, 0. Now that I know my tangent occurs twice, at t equals plus or minus the square root of 3, I have to figure out my equations for those. So what I need to figure out is I have my slope, and I just need to plug into my problem. So my tangent equations are going to be y equals the square root of 3, and then x minus 3, and y equals negative square root of 3, and then x minus 3. So to figure out the slope, we plugged into my original function, the dy over dx, and I just plugged in the square root of 3 to that, and then I'm also getting back out the square root of 3. So that's why those came out to be the same. Next up, we're going to look for the points where C has a tangent of a horizontal or a vertical. Now, to find a tangent of a horizontal, I'm looking for a slope of 0, and the vertical, I'm looking for a divided by 0. So I take my equation, the dy over dx. So if the dy is what I'm looking at, and dy is a 3t squared minus 3. Now that is going to be 0. So that slope is going to be 0 when t squared equals 1. So that means t equals plus or minus 1. So I have a horizontal tangent where t is plus or minus 1. I now have to plug that back into my original problems to find my x and my y. So if I plug in 1 to my original problem into x, I get 1. If I plug a negative 1 to it, I also get 1. And if I plug them into the y, I'm going to get negative 2 and 2. So those are the 2 points, 1, negative 2, and 1, 2, that are going to give me horizontal tangents. Now, to find a vertical tangent, I'm looking at where the bottom is 0. And so I get t squared, and I take the derivative of that. I get 2t. I set that equal to 0. and it only occurs where t equals 0. If I plug that into the other one, into the y, dy over dt, I do not get 0. So that is going to give me a vertical tangent. And when I plug 0 into both of my original problems, I get the point 0, 0. So this function has a vertical tangent at 0, 0. The next piece I want to find is where the curve is concave upwards and downwards. So to do that, I need to do the second derivative. So to determine the second derivative, I take the derivative of the first function, the derivative of the original derivative, and I divide it by dx over dt. So the derivative of my function is going to be 3 over 2 times 1 plus 1 over t squared. And then I take the derivative of the dx dt, which is 2t. So if I simplify that and work it out so it actually comes out to be a problem that I'm going to like, I get 3t squared plus 1 over 4t to the third. Now, we know that when we're looking at concave up and concave down, we're looking at where the top is going to be 0. That's where it switches. So in this case, look, the top is going to be switching at 0. So the t is greater than 0, it's going to be concave up. And if it's less than 0, it's going to be concave down. The last thing we want to do for this example is to sketch the curve. So I'm going to put all that information that I just got into the problem. So I plot my points. I plot my 3, 0, because I know that's on the graph. I plot my two horizontal tangents at 1, negative 2, and 1, 2. I plot my vertical tangent at 0. And then I plot my tangent lines, and this is the curve that we're going to get. Notice that I said if it was greater than 0, it's going to be concave down or up. And if it's greater than 0 or less than 0, it's going to be concave down. And this part right here is the concave down, and this part right here is the concave up. And because if you look at the arrows, this value here is below 0, and that value there is above 0. Next up, we're going to look at figuring out area. In this one, we're actually going to look at the cycloid. However, let's come up with the formula first. Now, if you remember, to find area, it's the integral of a to b of y dx. Now, that dx takes on new meaning because that dx is the derivative of the x function. So in this function, I basically have gt times the derivative of f of t dt. So that's why that dx is actually so important. It means the derivative of x, although in most situations we were talking about before, we didn't use it. So I'm going to look at the, for one area under the cycloid, so I'm going to go from 0 to 2 pi. So if you remember right, I have my original functions is x equals the radius times theta minus sine theta, and y equals the radius times 1 minus cosine theta. So I'm going to plug in the y, I'm going to plug in the r, and then I have to find the derivative of x, and the derivative of x is the radius times 1 minus cosine theta. So I plug those back in, and I have the radius squared. So I can pull that out because radius is, in essence, a constant in this situation. I'm doing from 0 to 2 pi of 1 minus cosine theta squared, because I go 1 minus cosine squared twice in there. So I'm going to FOIL it out. I get 1 minus 2 cosine theta cosine squared theta. And the reason I FOIL it out is because I've got to deal with that squared. So I'm going to change that cosine squared to 1/2 times 1 minus cosine 2 theta. So this way we can actually do the integral of it. I'm going to do the integral of all the pieces. So I end up getting 3/2 theta minus 2 sine theta plus 1/4 sine 2 theta. I'm then going to plug in from 0 to 2 pi into that function. And I end up coming out with 3 pi radius squared. And that's actually going to be my area under one cycloid for any radius. So I can change the radius now to anything I want, and I'll be able to figure out the area of that cycloid. The next thing we're going to look at is finding arc length of a parametric equation. So if we remember, the length of a curve is the integral from a to b of the square root of 1 plus the derivative of the function squared. So if we look at it in terms of what we have currently, we have the dy dt over dx dt is the dy over dx. Now, I want to clean this up a little bit to make it a little easier for us to work with so we don't have that fraction there. So you're going to find the common denominator, and you're going to end up getting dx over dt squared plus dy over dt squared, the square root of that dt. So this way, we have it as one simple equation that we can sit there and solve, finding the arc length. So that's the equation that we're going to use. Now, sometimes when you're looking at the arc length, when you're doing the integral, if you go from 0 to 2 pi, it actually doubles the arc length. So you have to be careful that you're only looking at t going through the equation once and not twice. So you might have to change the intervals for your angles or your t's to make sure that that doesn't happen. So let's find the arc length of one cycloid. So remember my x and my y. So we have to find the derivative of that. So the derivative of the x is the radius times 1 minus cosine theta. And the derivative of y is r sine theta. We plug those into the problem, and we get the square root of r squared times 1 minus cosine theta squared plus r squared sine squared theta, d theta. Now, I got to clean this up so this way I can put it all into the square root and do the square root of it. So we multiply it out and put all the stuff together, and I get 1 minus cosine squared theta plus cosine squared theta plus sine squared theta. Now the cosine squared theta plus sine squared theta is really just 1. So I really have 2 minus 2 cosine theta. So I can pull out the 2, and I pull out the r squared out in front, because remember, that's just a constant. So to evaluate this integral, we have to somehow make it so that we can actually do the integral in terms of, we have to get rid of the square root. So one of the identities that we have is sine squared x is 1/2 1 minus cosine 2x. It's pretty similar to what I have inside. So if we manipulate it around a little bit, I can get 1 minus cosine theta equals 2 sine squared theta over 2. So by plugging that in, I now have the square root of 4 sine squared theta over 2. So now I can do the square root of that, and I get 2 sine theta over 2 instead. Now we do the integral of that, which is quite simple, and we get the integral of that as negative 2 cosine theta over 2. We plug in 0 and 2 pi, and we get 2r is 2 plus 2, or 2 times 2 plus 2, which is 8r, is my arc length for my one cycloid. The last thing we're going to look at is surface area. Now, the surface area formula in what we're going to use is the integral from a to b of 2 pi y times the square root of the derivative of x squared plus the derivative of y squared. So let's look at an example. We want to show the surface area of a sphere of radius r is 4 pi r squared. So a sphere is as simple as taking a semicircle and rotating it. So to create a semicircle, I just do a circle, but I just do it from 0 to pi instead of 0 to 2 pi. So the circle is r cosine t, and y is r sine t. So we plug those values in to my integration formula, and we simplify it down. Now the square root of r squared sine squared t plus cosine squared t, that right there is 1. So the square root of r squared is just r. So I have the 2 r's that I'm going to pull outside, so I have the 2 pi r squared out front. And then it's just sine of t. The integral of sine of t is negative cosine of t. And I'm doing that from 0 to pi. So when I plug in 0 to pi, I'm going to get out 2 for that, which then I multiply by the 2 pi r squared, which gives me the 4 pi r squared. So that just verifies that the surface area of a sphere is 4 pi r squared, which we know from our geometry class.